Welcome to The Explainer. Today, we're looking at a massive, truly massive technological shift that has completely transformed our world in just a few short years. We're talking about the unprecedented ability of machines to actually process, understand, and generate human language at a scale we've literally never seen before. This isn't just about getting better search results. It's a foundational change in how we interact with technology. And, let's be honest, probably how you're already writing your daily emails.
So it brings up this absolutely fascinating question. How exactly did machines master human language? For decades, computers really struggled with basic grammar, mostly just doing simple keyword matching. But today they can write entire essays, analyze super complex software code, and even decode the fundamental building blocks of biology. To really understand how we arrived at this wild point, we need to look back at the problem-solution arc that drove this whole evolution.
Section 1. The Rise of LLMs.
Okay, so long before the modern AI boom completely dominated our news feeds, there were decades of foundational research. Back in the early 1990s, statistical models essentially just guessed words based on probability. It was pretty basic. Then, by 2013, we saw a huge breakthrough called word embeddings. This allowed computers to actually mathematically map the semantic relationships between words. Fast forward a bit to 2016, and neural networks were translating text. But, well, they had a fatal flaw, a strict sequential bottleneck. Basically, they had to read text painfully slow, one single word at a time. And that made training on massive datasets practically impossible.
Section 2. How language models work. Okay, let's dive into this. Because to really appreciate this technology, we need to look right beneath the surface. Now, the absolute first thing to know is that algorithms process numbers, not text. So how does that work? Well, text undergoes something called tokenization. It's chopped up into smaller pieces and mapped as numbers in this giant mathematical space. Imagine a vast, almost infinite 3D map. The model actually learns that a token like bark sits right next to dog in an essay about pets, but floats way over next to tree if the essay is about forests.
Right, so once it's tokenized, all that data enters the neural network. Now, remember those older sequential models we just talked about that choked on too much text? Well, the absolute game changer here was the transformer architecture. Instead of reading linearly, like you or I do, transformers process data in parallel. They take it all in at once. And this parallelization is exactly what allowed researchers to just completely blast past those previous limitations and train models on a totally unprecedented scale. And this brilliantly illustrates the heart of the transformer, self-attention. Think of it kind of like reading an entire page of a book in a single glance. It calculates the dependencies between all the words simultaneously. It assigns mathematical weights to figure out the context, even if two related words are, say, at completely opposite ends of a really long paragraph. This right here is exactly how the model captures such deep, nuanced meaning. So, you might be wondering, how do you actually train a model with this kind of architecture? Well, it happens in 3 main stages. Step 1 is pre-training. This is where the model analyzes trillions of words and simply learns to predict the next token. But let's face it, a raw next word predictor isn't actually all that helpful on its own. So step 2 is supervised fine-tuning, which is essentially teaching the model to follow specific instructions. And finally, we have step 3, RLHF, or reinforcement learning from human feedback. This is absolutely crucial. It aligns the model with human preferences, transforming a raw statistical engine into that helpful conversational chatbot you might use every day.
Section 3. Breakthroughs and turning points. So what specific research leaps triggered the massive AI explosion we're living through right now? Well, it all goes back to 2017 at the NeurIPS conference. A group of Google researchers published a landmark paper titled "Attention is All You Need." They introduced that transformer architecture to the entire world, fundamentally solving the computational bottlenecks of those earlier systems. It's no exaggeration to say this single paper literally sparked a global revolution.
Now, what's really interesting about this slide is that massive number, 175 billion. That is the actual amount of parameters. Think of them almost like internal mathematical brain synapses inside GPT-3, which was released by OpenAI back in 2020. This massive scale, which obviously required immense computing power and data, proved something incredible. It proved that simply making these transformer models exponentially larger unlocked shockingly powerful language capabilities.
And just look at how rapidly this builds up. From that foundational transformer architecture in 2017, we jumped to the massive scale of GPT-3 in just 2020. Then boom, in late 2022, ChatGPT brought this technology straight to the public through a really simple conversational interface, sparking widespread adoption. And by 2024, we saw the emergence of advanced step-by-step reasoning models. Honestly, the sheer pace of innovation here is truly staggering.
Section 4. Expanding capabilities and agents.
At this point, language models have completely broken out of simple text boxes. They're now interacting dynamically with the digital world. Through something called Retrieval Augmented Generation, or RAG for short, they actively browse external databases to pull in real-time information. They have tool use, meaning they can actually execute code. They're multimodal, easily handling images and audio, but fascinatingly, they even process non-natural languages. In computational biology, for instance, these exact same transformer architectures are being used to analyze protein and DNA sequences. They're essentially treating biological structures as a language just waiting to be decoded. How cool is that?
Now, when you combine all these expanding capabilities, you get what's called an AI agent. This is a real game changer because it transforms a passive text generator into a fully autonomous system. By integrating memory, decision logic, and external tools, an agent can take a really complex task, break it down, plan it out over multiple steps, and actually take real-world actions to achieve a specific goal.
Section 5. Limitations and societal impacts. Of course, this immense power doesn't exist in a vacuum, and it is absolutely vital for us to understand the structural risks involved here. The source material highlights several heavily documented limitations. First up, hallucinations. Models sometimes generate text that sounds incredibly fluent but is entirely false, driven by statistical extrapolation rather than actual facts. Second is algorithmic bias. These models can inherit and even amplify historical patterns from their training data, like assigning traditional gender roles to specific jobs. Third, we have copyright infringement, with major tech companies currently facing substantial lawsuits over their use of copyrighted training data. And finally, there are severe security vulnerabilities, things like prompt injection, where users can actively manipulate the system to bypass its built-in safety guardrails.
So the crucial point is, do these machines actually know what they are saying? There is an intense, completely fascinating debate among experts right now. On one side, skeptics argue that models are merely stochastic parrots, just complex statistical engines blindly recombining existing text probabilities without any true comprehension. Conversely, proponents argue that their ability to solve genuinely novel problems in coding and mathematics suggest an emergent, albeit totally unfamiliar, form of alien intelligence.
And we can't ignore that there is also a very tangible physical cost to this intelligence. To put that into perspective, check out the energy consumption per prompt. While simple data classification uses a tiny fraction of a watt-hour and text generation uses a bit more, generating a single image requires massive computational power, pulling nearly 3 whole watt-hours per prompt. As generative AI usage scales up globally, so does the harsh reality of its massive electricity demands and its growing carbon footprint.
Section 6. The future of AI.
So where is this technology heading next? Well, we are currently seeing a massive paradigm shift in how these models operate. Traditional autoregressive models are what we call next token predictors. They excel at lightning-fast pattern matching. But the new frontier, that lies in reasoning models like OpenAI's Okun 1. Instead of answering immediately, these newer models are actually trained to spend computational time thinking. They generate step-by-step logical analysis before ever producing a final answer, which drastically improves their performance on really complex coding, math, and logic problems. Simultaneously, the whole landscape is shifting from closed, proprietary systems to more globally collaborative efforts. A prime example of this is the rise of high-performance open-weight models like DeepSeek R1. This is a massive reasoning model that achieves performance comparable to the top proprietary models, but, and here's the kicker, it operates highly cost-effectively and allows researchers worldwide to study and build directly upon its underlying architecture. We've tracked the incredible journey from early statistical word counters to systems that can autonomously reason through incredibly complex logical problems. As these reasoning models continue to evolve and think step by step, where exactly is the limit to machine understanding? It is a profound question that will undoubtedly define the next era of human history, and one we will all be discovering the answer to together. Thank you for joining me on this explainer.